Good morning everyone, my name is Lee, and for today's video, we're going to be talking about two topics, the Knott-Morris-Pratt KMP algorithm and the Hamming Edit Distance algorithm. So in this video, the viewer will familiarize themselves on this topic and as well as will provide step-by-step demonstrations on how they understand and how they actually work. So whether you're a seasoned programmer looking to refresh your knowledge or a beginner eager to learn them, we will guarantee you'll walk away from this tutorial with a deeper understanding of these powerful string matching algorithms and apply them on what you have learned and also apply them in real life situations. Let's go! Before we start, let us first find out on what is a Knott-Morris-Pratt algorithm. So the Knott-Morris-Pratt algorithm is a string searching algorithm that efficiently finds all occurrences of a pattern within the longer text string. It was also developed by Donald Knuth and also Vaughan Pratt, with also improvements by James H. Morris, which makes it the Knuth-Morris-Pratt algorithm. Okay, so the key idea behind KMP is to use information from previously matched characters to avoid unnecessary backtracking while searching for the occurrences of the pattern within the text. So with this achieves through a construction of a failure function, or what we call in our terms a prefix function, which preprocesses the pattern string to determine how far to shift the pattern relative to the text when a mismatch occurs. So in more simple terms, the KMP algorithm helps find the word or phrase in a long text efficiently, and it does this by figuring out where to continue the searching if there's a mismatch between the pattern and the text. So this means that it doesn't waste time when rechecking things, and it already knows it won't match. So before we start this KMP algorithm, we need to first learn one of the most basic approaches on searching for a substring, which is what we call the naive approach. Naive approach. Okay, so we are given this question, which consists of text and a pattern. Text, it can also be considered as our substring. So in this substring, we are given the characters of x, y, z, p, k, l. And for our pattern, this is what we need to search for: z, p, k, and l. So how do we do this? Okay, so before we start, we need to give our substring indices, which is going to be 0, 1, 2, 3, 4, and 5. So these are the indices. Then we need to base off the first pattern, or we need to base from the pattern of the first character. So for our first character, with the index of 0, it is x. So x. So usually we need to put an I here, it's called an index as well, and here j, to know that if it's going to be similar. So since x and z are not the same and they're not compatible, this means we need to apply the rule of going to the next character since they do not have the same character as our pattern. J stays put while I, or index, goes to the next character, which is going to be y. So does y with the index of 1 match with j? No, it doesn't. So we need to apply the next rule, which is going to be that we're going to move it to the next one, while j staying put because there's no similar yet. So now we are here in the character of z with the index of 2. So does the character of z match with z? Yes, it does. So since it matches, we can consider this, and then we get to move j since they are similar. So j goes here and I goes to p. So the index of P with the number 3, since they both match, we do the same thing again. We're going to move them. Since they both match, we're going to be moving both I and J. So going to K, and then it's going to J is going to K. Next, L. So does L match with does the index of 5L match with the pattern of L? Yes. So since it matches, we need to move the index of I above L and as well as J. So since they all match together, this is going to be our substring, the index of 2 to 5, and this is our naive approach. So after explaining the naive procedure on how we can solve a substring, on how we can search the substring, we're now going to talk about the Knuth-Morris-Pratt algorithm. So we're given this example. This has a text, like I've said earlier, it is going to be our substring, and we're going to follow a pattern. So for the KMP algorithm, we always use a prefix table. So what is a prefix table? A prefix table is a lookup table that helps determine how far to shift the pattern when a mismatch occurs during pattern matching by storing the length of the longest proper prefix, which is also suffix, for each prefix of the pattern. As you can see here, we have 3 rows, which is the index, pattern, and prefix. The index is 1, 2, 3, and 4. The pattern C, A, B, and C. And now we have to calculate for the prefix. So for the character of C, there are no proper prefixes for a single character prefix, so the prefix length is always 0. Remind yourselves that the first character, or the single character, or the start, never has a proper prefix. So the length is always 0. Next is the index 2, which is equivalent to A. Once again, there are no also other proper prefixes for this single character prefix, so the prefix length is going to be 0. And for index 3, which is going to be B, there isn't a proper prefix for here as well, because it just doesn't have, and the prefix length once again is going to be 0. And now for index 4, the longest proper prefix, which is the suffix for the prefix, is the ending position, which is C, which has the length of 1, because it's the longest, and it's going to be based from here, from C to A to B and C. And now let's try to solve this substring. So for the first one, while we're trying to match, we can see that it already has a mismatch in index 1. So we then need to look at our prefix table and check for the pattern 1. Since it is 0, we then proceed like a naive approach. Like of what I've said earlier, a naive approach, we just go to the next one, meaning we don't have to do anything here. We just have to go to the next index and the pattern table. So once again, there's a mismatch again in index 2. We then have to look at our prefix table and check again for the pattern, which is pattern 1. And since it is 0 once again, we have to go to the next one. There is a mismatch again in index 3. We then have to look at our prefix table once again and check for the pattern since it's 1. So once again, since it's 0 again, we then have to proceed like a naive approach, and then continue this until we get a match for the pattern table and the substring table. So after doing all of that, we have finally found our first match, which is going to be index 9, which matches our pattern, CABC. So we then continue to proceed if the following characters ahead are also similar. So index 10, it's going to be a match again. So since they both match both ways, we then continue to proceed if the following characters ahead are also similar. The next index, 11, 11, also matches both ways. So we then continue to proceed if the following characters ahead are also similar. Since we already know what's going on here, we can practically say that we have found our first match, or our first match in the substring, which is then going to be the next one, which is next is going to be index 12. So we then continue to proceed if the following characters 9, 10, 11, 12 are also similar, and they are. The following pattern has been found and matched. We have finally found our first match in this substring, which is the index of 9, 10, 11, 12. As you can see, we can either return the text or go back to the start of the pattern or continue searching. But we're going to continue searching because at the end, there's also another substring or another potential match we can go up to. And since we found our matched algorithm, we don't need to start from where we came from, meaning we don't need to start on, let's say, we don't need to start from C on the index of 12. We don't need to do that anymore since we found our first match. Instead, we can skip that and go to the next index, which is going to be 16. And we can obviously see that it is not matched. So once again, we do the principle of naive approach until we can find the matched pattern to the index. We then continue the principle of the naive approach, and on index 19, they are both similar, as we can see here. They are finally similar. Since they're both similar, let us go on, proceed to the next one, and see if it's similar. We then find out that index 20 is a mismatch, and it does not match between here, the pattern, and the substring. So that means that, which leads us to the follow the pattern of 2, of this part here, the pattern 2. And while doing that, we have to figure out that it has a prefix of 0. It has a prefix of 0. So we need to implement the naive procedure once again, meaning we're just gonna have to switch the positions again. We need to go to the next one. And while moving on the index of 20, we then find out that both index and the pattern tables are similar. And as we can obviously see, we can finally achieve our next match and our last match. And those indexes are 20, 21, 22, 23. Once again, the index are counted by the top. They're mostly hidden, but they're also counted from the top, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is found here on the index of 20. And thus completing the entire pattern given. So for the summary of match strings, these are our following indexes. Our first index is 9, 10, 11, 12, and our last index is 20, 21, 22, and 23. These are our matched strings in this index of the KMP algorithm.
The approximate string matching algorithm we'll be talking about is the Hamming distance, or the Hamming edit distance algorithm. The Hamming distance algorithm is used to measure the number of positions at which the corresponding character of two strings is different. The Hamming edit distance algorithm is usually used for comparing two strings of equal length. Now let's play a spot the difference game. Say we're making ham and we want to replicate a recipe we found on the internet. We want to follow it to perfection, else we're just creating another recipe entirely. You plate it nice to your preferences and voila, you've got ham. Except it looks a little different than what you wanted it to be. Upon taking a second look at the recipe, you quickly notice a small contrast. That lime on the left shouldn't be there, and these two wedges are different, and the towel just looks a little out of touch. But we've still got time to fix our mistakes. We've determined our deviations from the recipe, so we know now the correct way to prepare our ham. These three differences we will correct are called the hamming edit distance. The hamming algorithm does this with strings, and it determines the amount of deviations in two given strings which both usually have the same length. Let's solve an example. We're going to take two strings with the same length, or with an equal length. We have 10110101 and 11010101. We're going to compare the first character, 1 and 1. Well, these two are the same, so we're gonna move forward. Now 0 and 1, are these equal? Well, 0 and 1 doesn't match, so the edit distance so far is going to be 1. Next character, 1 and 0. It also doesn't match, so we're gonna increment 1 to our edit distance. Going through the rest of the array, we can see that the characters are equal. So the hamming edit distance for this string in total is going to be 2. We're going to insert it to our code here, and yep, the hamming edit distance for these two strings is 2. We can see that the algorithm works in linear time and is represented by the big O notation of n, because the I value depends on the user input, or is determined by the user input. Now let's take another example. Algorithm and rhythm. Well, notice that these two strings have differing lengths. Rhythm has 3 less characters than algorithm. How the hamming edit distance algorithm works with these two strings is that it takes into account the number of additional characters in the longest string and starts with comparing the first character of each string and then it moves on to the next. Starting with the first character of each string. Is A equal to R? Nope. Let's add 1 to our distance. Moving on to the next character, L and H. They're not equal. So we're gonna put increment 1 to our edit distance. Well, G and Y are not equal. Neither is O and T, R and H, and I and M. And neither are all of the extra characters. Therefore, the hamming distance between these two strings is going to be 9. We're going to plug it into our code and yep, we can see that the hamming distance of these two strings is 9.
Now, how the hamming edit distance differs from the Levenshtein distance is that the Levenshtein distance usually focuses more on addition and substitution operations. If we plug the strings algorithm and rhythm into a Levenshtein algorithm, the hamming edit distance of the two will be 6, and we've noticed that is because of differing string lengths. We've noticed that the hamming edit distance works best on strings with an equal length, and the hamming edit distance algorithm is relatively simpler compared to other conventional string matching algorithms, but it still plays a valuable role today in error detection in data transmitted over computer networks. And I believe that is it for the Knott-Morris-Pratt and hamming edit distance algorithm. This should be a relatively simplified representation of how the KMP and hamming edit distance algorithm works. We hope we've explained everything clearly and that you enjoyed the presentation.